Okay, everyone. So the live stream should be live now, and you should be able to see this. So if you can give me a sign of life, a thumbs up or so when this gets to you, that will be great. Okay, very good. So we'll just give it another half a minute or so for people to trickle in from the groups. So today we're going to continue talking about kinematics, which is the topic we'd started on last week, Friday, right? We talked about displacement and we talked about position. So now we're going to introduce a couple of other concepts. So we're going to introduce average velocity, instantaneous velocity, and speed. And in particular, we'll talk about what the difference is between speed and velocity. This will be, of course, very similar to the difference between displaced I forget what we called it, a traverse distance and displacement. So speed will be essentially the equivalent of I can't remember what we call it, of traverse distance, let's call it that. So speed will take that similar role. And then we'll introduce also acceleration, average acceleration, and instantaneous acceleration. And from that, we'll be ready to actually start doing some problems, or at least start doing some examples of problems. So let's get started. We talked about this already, about position as a function of time. So if we have a car, or I think we used the example of a professor pacing around a room. So the professor is pacing around the room, or this was the example of the person leaving from home, going half a kilometer in one direction. After 10 minutes or 8 minutes, they arrive there. Then they go back for half a kilometer, end up back at the original position at home at 0. Then walk 1 kilometer in this direction, and then back 1.75 kilometers in the opposite direction. So if we put that on a graph versus time, we of course see these. We see this behavior where we start at 0, go to 0.5 after a certain number of minutes, back to 0, up to 1, and back to minus 0.75. So this is something you'll need to do in one of the next problems is come up with these kind of graphs. Of course, there's information we can draw from these graphs. In particular, we'll be able to see at what position this person Jill is at any given time. So that's one thing we'll be able to read off from that graph. The other thing, so this will be indeed on the next homework assignment. So the other thing that we can read off from that is actually the velocity, the average velocity to get, for example, from the first point from home here at 0, 0 up to the first point at 8 minutes and 0.7 and 0.5 kilometers. So that will give us, if we take the difference in position, or in other words, the displacement, and divide that by the elapsed time for that interval, that will give us the average velocity. And so that is one thing. Well, let me just make sure I got my notes on the right page here. So that will be one thing that we'll want to determine is the average velocity. So if we want to do that as a formula, the average, sorry, give me a second. I need to set my tablet to the right interface. Okay, this one and this one. Okay, so the average velocity is the displacement delta x over delta t, or if we write that in words, the displacement over the elapsed time. So if we go from point A to point B, that gives us the displacement delta x, which will be a vector quantity. And if it takes us delta t time to get, if we cross this in time delta t, if this is for example t0 and this is t1, delta t will be t1 minus t0. So then the average velocity will be delta x over t1 minus t0. Okay, so none of that should be that spectacularly new, because you might have already seen that before, right? So we can calculate the average velocity for this stretch where the velocity is constant, the average velocity for this stretch, which will have a constant velocity, and then a third stretch and a fourth stretch, each of which will have a different average velocity. We can also calculate the average velocity from the start to the end, which will be the displacement, which is minus 0.75, divided by the elapsed time, which is 57 minutes, for example. So that will be the average velocity for this entire problem, for this entire stretch of time, and all of the movements in between that. You'll see that that average velocity, of course, will be different than the average velocity for each of the individual steps in the problem. So now, when we talk about average velocity, that gives us the velocity over a certain amount of elapsed time, and for a certain finite time in particular. So if we look at t1 to t6, that distance, if we look at the position versus time graph, the difference in position from t1 to t6 gives us the displacement. And if we divide by the difference in time, the elapsed time between t1 and t6, that will give us the average velocity that's given by this line here. The slope of that line is actually the slope of the time the slope of the graph is going to be this average velocity. Now, if we take this time interval shorter and shorter, we bring t1 closer and closer to t0, and t6 closer and closer to t0. At some point, we'll get the tangent line here. And that will give us now not the velocity, the average velocity between two different points in time, but that will be the instantaneous velocity at that single point in time. So the instantaneous velocity is now instantaneous velocity. So that's literally what we get if we take the limit for delta t going to 0 of delta x over delta t. So, and we'll just call that the instantaneous velocity v as a function of t. Now, this is something that applies at a single point in time. And as you know from calculus, this is nothing else than the definition of d dt of the position versus time, the position of a function of time. So the first derivative of the function of position versus time is going to give us the instantaneous velocity. So the first derivative of this curve here will give us the instantaneous velocity v as a function of time. Again, those are things that probably are not necessarily new to you, but are important to remind ourselves of. Okay. So we can look at now a couple of different graphs, of course. Let's look here at this first graph on the left. That's a position versus time graph. So we see a couple of points indicated here, one at 0.25 seconds approximately, at 0.5 seconds, one at 1 second. We can see that the position starts at 0, becomes positive, then goes through 0, and becomes negative. We can look at the velocity, which is the first derivative of this position versus time graph, which is the slope of this time graph. So we start off with a slope that is positive. At this point, the displacement, if we were to take that limit here, and in particular if we compare between the point at the origin and this first point indicated here as 0.25, the displacement is positive divided by an elapsed time, that's 0.25, so that's going to be a positive quantity for the average velocity, and if we take the limit, that will also be a positive instantaneous velocity. When we get to the highest point here, or I say highest point, the highest in value for the position, so this is technically we're talking about x here, so typically this would be horizontal movement. If we talk about vertical movement, we'd use y or z, even though those are of course conventions. But when we're at this point at 0.5 seconds, now the slope is horizontal. The slope is 0, the tangent is horizontal, so the instantaneous velocity is going to be 0. And as soon as we're past that point, the instantaneous velocity becomes negative. We go through the point at 1 here. As you can see, there's nothing special about this point at 1 in the velocity versus time graph. Just the instantaneous velocity just keeps becoming larger with a negative direction. And here it's also continuing to be larger and has a negative direction. So this is the instantaneous velocity in panel B here in the middle. And now we can introduce also the concept of speed, which in daily life you would use probably speed and velocity as interchangeable terms for the same thing. In physics, of course, that is a different thing. In physics, velocity is the vector quantity that has a directionality to it, and speed is the magnitude of that vector quantity. So it's the absolute value of the velocity. As you can see, if we take this curve and we have our negative velocities here, if we take the absolute value, then we'll just get the curve on the right as indicated with the speed here. So the speed is always positive. The velocity can be negative and positive because it will have a different sign. So if I ask you now, we can have one thing that is important to realize is that there's a difference also between average speed and average velocity. Let's consider the points at time 0 and time 1 here. At time 0 and time 1, we have the same velocity but pointing in the opposite direction. If we wanted to calculate the average velocity between points at time 0 and at time 1, the displacement is 0 at both times. We're at the same position 0, so the displacement is 0, and over that elapsed time of 1 second, that would give us an average velocity that's equal to 0. So we have an average velocity that is equal to 0. Now over that same time interval, the average speed is not 0. We would take the average of the speed that is decreasing here and is increasing here, but since the speed is inherently always either positive or 0, if we take an average over an interval where the speed is at some point non-zero, we will end up with a positive number. So between time 0 and time 1, there's an average speed that is non-zero, even though the average velocity is 0, and the instantaneous velocity has a part that is positive and then a part that's negative, or a duration of time when it's positive and a duration of time when it is negative. So I essentially covered the answer to this question already. So are the average speed and the magnitude of the average velocity always identical? Well, no, they're not. For example, in this case, where the average speed will be non-zero here and the average velocity between time 0 and time 1 will be 0. So this is not the case. And when this is not the case, it is the case, again, similar to the question we had on Friday. It is similar to the solution then, which is if it's always in the same direction, then that will, of course, when the speed is always equal to the velocity, in other words, when the velocity is positive, then the average speed and the average velocity will be the same. So just to put everything together on displacement, velocity, and speed. So we have our displacement, again, the difference between the positions from a final and an initial point. Total displacement is just the sum of those vector quantities, the sum of those displacements. Average velocity is the displacement over the elapsed time. Instantaneous velocity is when we take that elapsed time and take the limit going to 0, which gives us the derivative of the position function. And an average speed is the absolute value of the velocity, absolute value of the average velocity, so total distance over elapsed time. And then instantaneous speed is instantaneous speed is the absolute value of the instantaneous velocity. Average speed talks about total distance traversed over elapsed time, and is not necessarily identical to the absolute value of the average velocity. So now that we've talked about speed and velocity in particular, let's talk about acceleration. So acceleration is to speed, acceleration is to velocity what velocity is to displacement. It's or what velocity is to position, rather. So acceleration is the change in velocity over elapsed time. So if we look back at average velocity here, it's the displacement over elapsed time. Now average acceleration is going to be, and so we'll call this A average, is the change in velocity over elapsed time. So change in velocity over elapsed time. So if my velocity changes from, let's say it changes from an initial velocity that is plus 2 meters per second, it changes to a final velocity that is minus 2 meters per second. In this case, just the vectors have the same size, so I'll use the same magnitude. Then my acceleration will be that plus 2 meters minus minus 2 meters, so 4 meters per second, divided by the time, the elapsed time between when it has this velocity going in the eastern direction and when it has the velocity going in the western direction. So again, we can make graphs. So we have here our graph of velocity versus time. This is actually the same situation we just looked at. This is exact same graph here. So going from plus 3 to minus 3 over a time of 1 second. So now we go from plus 3 to minus 3 in this time of 1 second. So that means that our change in velocity is minus 6 meters per second over the time interval, over an elapsed time of 1 second. So that will give us minus 6 meters per second squared as a unit, as a constant acceleration during that interval. Right. So this is our average acceleration between time 0 and time 1 is minus 6 meters per second squared. Now, of course, we can also turn this into an instantaneous acceleration, just like we did with instantaneous velocity. So in instantaneous acceleration, and I'll let you guess what that is defined as. A as a function of t is of course the limit for delta t going to 0 of delta v over delta t, or that's the time derivative of the function of the velocity function as a function of time. So the time derivative, or the derivative of this curve, will be our acceleration, right? So that's our acceleration. In this case, this is instantaneous acceleration, which happens to be constant, which is why, of course, for our average acceleration over any interval, we would find the same as the instantaneous acceleration anywhere along that interval. So indeed, if you put everything together now, so we've got x as a function of t, then v as a function of t is d dt of x, and then of course a as a function of t will be d dt of v, or d2 dt squared of x as a function of time. So we've got our second derivatives to the time of the function of x. So let me also point out that in this case, we actually changed our acceleration, or we changed our velocity from a positive value to a negative value. We call this in physics also acceleration, even though, again, when you talk to someone who's not in this class, you might use the word deceleration. Deceleration is not a physics word. It is a word we use in daily life. We will call this negative acceleration. So negative acceleration is what we get when the velocity changes in the opposite direction as the initial velocity. So in this case, if the velocity changes in the direction opposite to what it's pointing at, then, so in other words, it gets smaller and then changes sign and becomes larger in the opposite direction, then we'll have negative acceleration, which you might think of as deceleration. So again, examples, a train that's stopping will have an acceleration that is pointing opposite to its initial velocity vector. A train that's accelerating in the traditional, in the common English understanding of the word, will of course have an acceleration vector that is in the direction of its velocity, because it's going to increase the size of that velocity vector. So the difference between two consecutive velocity vectors will be along the direction of that and in the direction of that velocity, because it becomes larger and larger. So a question to consider, what is the sign of an acceleration that reduces the magnitude of a negative velocity? So now I've thrown in another sign. I've started off with a negative velocity, and we want to know what the sign of the acceleration is that reduces the magnitude of this negative velocity. So let's go with 1 for positive, and let's go with 3 for negative. You see a few answers, but not too many. So 1 for positive, 3 for negative. I see a lot of ones in the chat. Okay, so let's work through this. So we have a magnitude of the velocity, or we have a velocity that is negative. So if we draw this out, we start. You know, this is our direction. This is our axis, or x-axis. So we have a negative velocity. This is our initial velocity vi, and we want the magnitude to be reduced. So v final could be this, v final, right? So the difference between vi and v final will be this, the change in velocity, and so delta v over some delta t will be pointing along the positive x direction. So the sign of that acceleration will indeed be positive. Okay. So another question, when is velocity 0 but acceleration non-zero? Is that something that can ever occur? When is velocity 0 but acceleration is non-zero? This isn't really a multiple choice question, so So can this happen? It actually can happen because we already saw an example just now, right? So if we go back to one of these plots here, let's go to this one here. So we have a velocity which started off being positive, goes through 0, and becomes negative. So the velocity changes sign around 0 here. But the acceleration is non-zero. The acceleration is always minus 6 meters per second squared. So what's happening here is that in the first part, until half a second, the velocity is pointing in the positive direction. In the second part, the velocity is pointing in the negative direction. And so this corresponds with exactly this kind of behavior where we're changing direction, where we're going first in the positive direction. And this is the point where the velocity is 0, but the acceleration is non-zero. There's a non-zero second derivative of this curve if you want to put it in calculus terms. And so we start to go back in the negative direction. We're not immediately in the negative position, we don't immediately have a negative position, but we immediately have a negative velocity, and that negative velocity is increasing in magnitude as we get further in time. So going back to the question here, when is the velocity 0, yet the acceleration is not? It's when we change direction from moving in the positive direction to moving in the negative direction. And in particular, when we do that, of course, in a continuous way so that we have a velocity that is instantaneously equal to 0. So typical magnitudes of acceleration. So you might have a kind of a feeling for what magnitude of velocities are common in meters per second. So I didn't introduce those. But magnitudes of acceleration you might not have as much feel for. So typical magnitudes when you take a train is less than 1 meter per second squared. An elevator that accelerates a bit faster. So that's 2 meters per second squared. Objects in free fall, which we'll talk about a lot on Wednesday, are falling at about 10 meters per second square. And then if you go to some very high accelerations that humans are subjected to, then an ejection seat from an aircraft, and you're subjected to 150 meters per second squared, which is of course something that literally can drain the blood out of your head and make you lose consciousness for a while. So those are high accelerations that are not, let's just say, not recommended. This is exactly the same graph as we talked about already before in the case of instantaneous velocity. So again, instantaneous acceleration is going to be the tangent of the function of velocity as a function of time. And again, we can do the same kind of approximation where we take different intervals, t1 through t6, t2 through t5, t3 through I shouldn't have used a tongue twister to explain this. So we can use shorter and shorter intervals and take the limit essentially of our delta t to get to this, to get to the limit of the slope of this tangent line. So in this, these are really just similar plots and sort of reinforcing the same concepts where we have our velocity that's going in the positive direction and is now going in the negative direction. The difference here is that we're looking here at this graph. This is a velocity graph. So this is not the position graph as before. This is a velocity graph. And now we don't have a constant acceleration, but we have an acceleration that decreases and changes sign. So we have a velocity that is at its maximum here. When the velocity is at its maximum in magnitude, that will be when the acceleration is 0. So think of this as very similar to the x and v plots that we saw earlier that looked exactly the same, but now it's in the velocity and the acceleration. So one thing you might want to think about is, okay, what is the position going to look like? So that requires that we take this velocity graph versus time and construct a position graph such that this velocity versus time graph is the derivative of that position graph. So I'm not going to ask you to do that. That would be requiring you to draw some third order polynomials. But you would be able to do that. And one example this shows here, of course, is that the acceleration doesn't have to be constant. We can have an acceleration, an instantaneous acceleration that varies versus time. In this case, it varies linearly. That's, of course, not required. So in this case, it's a linear decreasing acceleration that actually changes sign here as well. So now let's think a bit about the problems that we can solve with these kind of with this kind of insight, right? So I'm going to go back to the whiteboard here, because this is going to be something we can work through some formulas for. So if we have at a time t equal to 0, if we know that we're at position x0 with velocity v0, and let's assume in this case that we're working under constant acceleration. So the acceleration here is a and doesn't change. At some time t greater than 0, we'll have a position x, a velocity v, and again still the same acceleration a. So this gives us delta x is x minus x0. That's our displacement, right? We can get our delta v, which is v minus v0. That's our change in velocity. And of course, there's no change in acceleration. So let's look at what we can do with this. We can write that our average velocity, which was our displacement over the elapsed time. Obviously, we can also write delta t is just equal to t minus 0, so that's just equal to t, right? We could have introduced here a time t0 instead of t, but that would have just made the math a little bit onerous to write, so I'm not going to write that. So the average velocity is delta x over delta t, or x minus x0 over t. The average velocity is also equal to v0 plus v over 2, just the average of the velocities, right? The average velocity is the average of the velocity. So let's look at what we got here. This has to be equal to that. So we can rewrite these things. Well, first of all, what we can do is we can write that x is equal to x0 plus v average times the time. That will be an important equation to keep in mind. If we now look at both of these, so we can plug in the average velocity into this equation. So x is x0 plus v0 plus v over 2 times the time. So now we've written the average velocity in terms of that initial and final velocity. So that will be another equation that we'll want to keep in mind. And there's one more that we have to write down. This is not based on the average velocity, but based on the average acceleration. And since there's only constant acceleration, this is just going to be the acceleration itself. So the acceleration is delta v over delta t, and delta v is v0 is, I got a typo in my notes here. So that's v minus v0 over the time. So that gives us that v is v0 plus a times the time. So that's another important equation we'll want to use. We can use this expression and plug it into this one for v, and that will give us that x is x0 plus, and then we can go through and see what's included in that equation. So we'll have v0 plus at divided by 2 times the time. So that gives us x0 plus v0 times the time plus 1/2 at squared. And that's going to be, again, an important equation to keep in mind. So the first one gives us here x as a function of the original position, the average velocity as a function of time. Then here we have the velocity in terms of the initial velocity, the acceleration, and as a function of time. And now we have the position in terms of the initial position, the initial velocity, the acceleration, and time, right? So those are going to be important equations to keep in mind, because these are the ones that we're actually going to have to use to solve problems. And one thing I'll put explicitly here is that this relies on having a constant acceleration in both cases. Constant acceleration. So the first thing to keep in mind is that we have to, that these equations are only going to be valid when we have constant acceleration, right? They're not they're not going to be valid for cases where the acceleration is not constant. So when you have a problem, first try to ascertain that that it is indeed a problem with constant acceleration. Okay, so there's one more formula that we need to derive here, and that formula starts off from this expression here, where we write the velocity in terms of the initial velocity plus the acceleration times the time, and we use it to derive the time. So if we start from that equation, we can write that the time is equal to v minus v0 over the acceleration. So in other words, this tells us what's the time that it takes to get a certain change in velocity given a certain acceleration. So if we have that time, and we combine this now with this formula here, x minus x naught is the average velocity times the time, or in other words, x minus x naught is the average velocity times the time. We can now write this as v0 plus v over 2, that's the average velocity, times the time. Well, we've just determined what the time is, so this is v minus v naught over a, or this will be 1 over 2a times v squared minus v naught squared, just using algebra of the product of these two terms with opposite sign. Or we can write this as v squared is v naught squared plus 2a delta x, or 2ax minus x naught. So that's another important equation, again only valid for constant a. So why would we use these equations? Well, of course, this one doesn't involve the time, the last one we've determined. So this will be, for example, an equation we would use in the case of determining the stopping distance. So we're not asked here, so this is a car stopping in front of a red light, and the question is, given the initial velocity and the final velocity, hopefully 0, and the acceleration, what is the distance it takes to change the velocity from 30 meters per second to 0 meters per second? And this is, of course, where that last formula will play a role, because it doesn't require that we know what the time is. We aren't asked for the time, so we can use the formula that doesn't require that we determine the time. So we'll start with that on Wednesday, a problem similar to this, and then we'll continue from there. In the slides, I'll point out one thing which I unfortunately can't play here on YouTube, because it probably get the YouTube streaming unlisted. But there's an interesting song from They Might Be Giants that talks about the difference between speed and velocity, and I encourage you to listen to it to make that concept clearer. And that is it for today. So if you have any questions, tomorrow afternoon I'll have office hours, so feel free to stop by there then. Bye everyone. I'll be hanging out here in Gathertown a little bit.